Now, your test 3 is going to be very similar to this. Okay, write the electronic configurations of the following. Okay, lithium. In fact, let me pull up a periodic table. Okay, so lithium is located right there. So you're looking at 1s2, 2s1. Tin. Now, tin is SN, and it's an old Latin term for tin, but it's SN. So let's find tin now. And tin is over here. Okay, that's on shell 5 now. So we're looking at 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. Now, the other way to do it would be to insert the nearest noble gas, which would be krypton. So let's do it both ways. Let's do the short one first. Okay, so we're 2 into the P's at shell number 5. Okay, then we're going to do the long way. And it's a really long one. And so we're looking at basically this here is electronic configuration for krypton. Those are the valence electrons. These are the core electrons. Remember, valence electrons is what runs the reaction. They're the most unstable, and they want to become more stable by reacting, either coming, going, or combining. Copper. Are there any questions about that? For this class, that's about as complicated as it's going to get. When you get into 1A or 2A, they're going to get more complicated than that. But the main thing is to be able to write some stable, simple electronic configurations. So when you're going into your next class, it'll just be just extending that a little further. Okay, and copper, where's copper? Copper's right over here. Let's get rid of some of this stuff here. Oh, that's in the D's, the 3 D's. So we're going to say AR. Let's do the simple one first. So argon is the nearest noble gas, up one, over here. And it's 9 into the D's. Okay, if we're gonna do the long version, it's gonna be okay, so that would be the long version. Okay, determine what elements are donated by the following electronic configurations. So the easiest way to do this is to just look at the valence electrons. These guys here. 3s2, 3p6. So 3s2, 3p6. So it's argon. Okay, so valence. Oops. Yes, I know. Yep, I am. Okay, so the next one. 5s2, 3d3. Okay, so 5s2, excuse me, 4s, over here. 5s2, 4d3. 1, 2, 3. So it's Vivian. Okay, determine which of the following electronic configurations are not valid, then correct it if it's not valid. So point is, some may be valid, some may be not. Okay, so let's look at this. 1s2, that's good. 2s2, 2p6, 3s2, 3p6, 4s2, 4d10, 4p5. Okay, so that should be 3d10. The 4d10. So that's the one that's wrong. Okay. Let's look at this guy here. A little bigger here. Okay, 1s2, 2s2, 2p6, 3s3. Now you could do this one of you could do this a couple different ways. You can just correct it, or you can count the number of electrons and make the electronic configuration consistent with the number of electrons. So there's two answers here you could do. Okay, any questions about the electronic configurations? Yeah, the S's need to be just two. One or two, never more than that.
How instead of like if it
So the D's are down 1. So as you're going across, so if you're starting in shell 4, the D's are going to be all 3s. Yeah. And if you start in shell 5, then the D's will be 4. Now, when you get to 1A or 3A or whatever, you're going to find the F's are down 2, not 1. So if you start in shell 6, then you go to 4F, down 2. Then you go to 5D and then 6P. But don't worry about F's. The main thing is the D's. They're down by 1. Yeah. Just remember dumbing it down by 1. F, or even worse, down by 2. I'm sorry, I have to have these tricks because of two reasons. One, I've never been good at memorizing stuff, and 2, I'm old. I have to have gimmicks. All right. Any other questions? Yeah. Well, I've already done the test, and normally teacher would say, well, you need to know that. But no, you don't. It's basically be very, I don't like, when I was a student, I hate when teachers would throw things and then like, well, you just have to know it. I didn't cover it in lecture, just make sure you read it in the textbook. I don't like that. So when I give you a practice test, basically your real test is going to be very similar to the real thing. You're taking OChem from me, it's the same thing. Biochem from me, same thing. Here's a practice test, know that inside and out, and you'll do fine on the test. So on the practice test, there's no core versus valence electrons. Know though that valence electrons is where all the chemistry is, except for nuclear chemistry. Because those are the most unstable electrons, and they want to become more stable. How? By reacting. The core electrons are already fine. They're super, super stable, so those never change, no exceptions. But you won't have to identify core versus valence. Although next semester, I just may with say again really loud. Yeah, either way. Yeah, whatever way you feel most comfortable with. Normally, classes always cover the long way first, and then they show you the short way, just so you know where it comes from. But yeah, you can use a short way, it's fine. All right, so let's go ahead and go on. All right, name the following. Now, naming, we need to go, is this ionic or covalent? And then you need to use the appropriate naming convention. Okay, so okay, iron sulfite. Okay, if you look down your common ion chart, which I'm going to give you for the test, you'll find that iron is in 3 flavors, plus 1, 2, and 3. Sulfite, SO3, you'll notice it's -2 only. And we have 2 of them. That means the sulfites are -4. So what does that make the iron? Plus what? And on your common ion chart, it's not there. But remember, common ions means there are non-common ions as well. So what forces the iron to be? Plus 1, 2, 3, 4, 5, 6, 7, 8. What is it? 4. Because you have to balance it against the -2 twice. So -4 +4. So that makes that iron 4. Sulfite. Okay. Now, the common ion chart is a guide. Yeah. 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 That would be crazy, wild. But yeah, your example, exactly. Yeah. So if you look up SO3 in your common ion charts, -2, we have 2 of them. 2 groups of -2s. All right. We have aluminum sulfate. Now, sulfate is SO4 -2, and aluminum is +3. Now, aluminum only exists as +3. Doesn't exist as +2, whatever. It's only +3. Okay, so we have 2 aluminums, that's +6, 3 -2s. So all that is aluminum sulfate. Notice I didn't put a 3 there. If you want to put a 3 there, that's fine. But you don't need it because it doesn't exist except for +3. Now remember, the ones that exist in multiple versions are in the middle. These guys exist in multiple versions. Those require a Roman numeral. The ones in the middle. And again, the reason is, even though some of them are usually, like zinc is always +2, always. But it can exist as others, but normally it's a +2. So sometimes they'll say, well, zinc doesn't count, but just in general, and there's some exceptions, but in general, the ones in the middle, put the Roman numeral in. The Roman numeral is always optional in my class, just for clarity reasons, but depends on who you get next. It may not be optional. Okay. And then lastly, we have K3PO4. K is +1 always, because it's not in the middle. And PO4 is a -3. That's why there are 3 K plus 1s to balance the PO4. So all this is potassium phosphate. Now you're going to find when you get into biology more, phosphate is a very important biochemical. It's all over the place in our bodies, even though it's a fairly strong, it's one of the strongest weak acids. I don't know if that makes sense or not. Okay, so what are the formulas for the following? Okay, mercury 2 chromate. Okay, so mercury is Hg. Right over here. Okay, and that says it's +2 charge. Now, if you look on your common ion chart, you'll find mercury 2 is a +2. Now, mercury 1 is also +2, but it's got two of them. That's what makes it +2. Okay, and then we have chromate. Okay, mercury +2 balances the chromates -2. So the formula is HgCrO4. Parentheses are optional because there's just one of them, but if you want to put it around it, that's fine. Okay, we have iron 3 bromide. Okay, iron 3 is a +3. That's what the Roman numeral 3 means. The bromide is a -1. So it's going to be FeBr3. So we balance out a net zero charge. Okay, this should be, by the way, heptos is 7. So that means we have 7 oxygens. Penta is 5. We have 5 of those. Now, because we have oxygen and sulfide, they're 2 anions, 2 nonmetals. That means it's molecular or covalent convention. No charges involved at all. Okay, so any questions about nomenclature? Yeah. Yeah, our question is, you get the common ion chart for the test? Yes. And you'll get the reactive series and you'll get the solubility table, all 3 of those. All right, calculator time. How many moles of H2SO4 sulfuric acid are in 2.34 moles? Okay, so our given is moles. We want to calculate, oops, excuse me, our given is grams. We want to calculate moles. So what's the conversion factor we need to use for going from grams to moles? Yeah. It is 1-to-1, but that's unit 4. All we're going to do now is use the molar mass. Remember the molar mass? Where does that come from? What do we need to find the molar mass for H2SO4? The periodic table. Okay, H2. Okay, 2 hydrogens at 101 apiece. 1 sulfur. Sulfur is 3207. 4 oxygens at 16 apiece. Yep, exactly right. So that is 34. I'll look. And that's grams per mole. And that is the molar mass. So that's our conversion factor, going from grams to moles, moles to grams. Okay, so we have you gotta remember the 3411, was that right? Is 3411, I'm trying to remember what 30.11, okay. All right. Moles cancel gives us grams. Okay. Sig figs, is that correct? Yeah. No, it's well, it was small. Yeah. 3411. Okay, two H's, 101 apiece. But there's two of them. Okay, so that's 202. One sulfur is 3207. Four oxygen at 16 apiece. That's 64. Yes, that's not 34, is it? Ah, yeah, 9809. And so our answer is not 79. What's the sig figs on our answer? How many sig figs should we have? 3. So the answer is going to be that's going to be what, 230. Okay, and we need to put a period there to make it 3 sig figs. Period is required, a decimal point. 23.0 is 2 sig figs. So make sure your sig figs are consistent. Okay, so we have how many grams of H2SO4 is 3.45 times 10 to the 34 molecules. So That's the given. What's our first conversion? Molecules to moles. Good. Okay. How many molecules are in a mole of anything? Avogadro's number, 602 times 10 to the 23rd. Okay. Now we have, oops. Now we have moles. Now we need to go to grams per mole, which is our 9809. So moles cancel, gives us grams. So we have and we have 3 sig figs as the answer. So it's going to be 5.62 times 10 to the 12th. Big number. That's 1,000 billion grams. Okay. How many H atoms are in 4.223 grams of ethanol? Okay. C2H6O. All right. So we start with 423 grams. In fact, let's do this. Okay, first step is grams to moles. So C2 is 1201 twice. 010 is 16. And then 6. What is it? 6 hydrogens at 101 apiece. Okay, so that's 2402 plus 16. Okay, that gives us moles. Now we're going to go to the number of molecules of ethanol. So we need a 602 times 10 to the 23rd molecules per mole. And then the last step is the ratio of H atoms per 1 molecule, which is 6 to 1. Okay, does everyone see where I got the 6 from? Because each molecule of ethanol has 6 hydrogens in it. So we have to multiply the number of molecules times 6 to find out how many hydrogens are within that. Okay, so the 3.32 times 10 to the 23rd hydrogen atoms. Bless you. Okay, balance the following. Okay, so first thing we do is an inventory. Okay, so we have 4 carbons, 10 hydrogens, 2 oxygens, 3. Okay, so let's make it 4 carbons. That's going to make that 11 oxygens. Let's make this 5 hydrogens. I mean 5 waters, so it kicks that a number of hydrogens up to 10. And then we have 13 oxygens. Okay, so let's on the left side convert O2s to 13. So we're going to multiply this by there. Now balanced. Now we have a fraction, we cannot leave it that way. So to clear the fraction, we multiply everything by 2. So it's going to be 2, 13, 8, 10. And don't forget, you have an extra credit equation balancing as well. Sydney, did you try that? Huh? Using the matrix method? And did you show it to your dad? Since he remembered the matrix method? All right, any questions about the balancing? All right, for the following chemical reaction, balance write both the molecular net ionic equations. All right, so this is a salt and a salt, which is a double replacement reaction. So now we're going to need the solubility table. Okay, so that means the lead goes with the chlorine. It's up here. Now, what's the charge on the lead? Well, carbonate from your common ion chart is a -2. And we have 2 of them, so that makes that's lead 4. That means we're going to need 4 chlorines to balance that off, since they're -1 apiece. And we don't know if it's aqueous yet or not. So we need to look at the solubility table. And then we have potassium carbonate. And we need 2 Ks because carbonate is a -2 from your common ion chart. Okay, so let's go to the solubility table now. And we have chlorine right here. And lead, where is lead? Lead's over here. So it's black. That means it's a solid. That's what we're going to do in lab today. And potassium, everything with potassium is always aqueous. So that's the molecular formula, balanced. Okay. The net ionic, did something happen? Did we form a solid? Yes. So that's in the net ionics. So that's this here. So we have and then the spectator ions are going to be the Ks and the carbonates. So that's what we're doing in lab today. We're going to be going dropper, 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 dropper. What, anything happen? Yes or no? Look it up in the solubility table. That's the prediction. Then verify it with your observation. Okay, balance and explain whether the following equation will happen. Okay, now this is a single replacement because it's a metal and a salt as opposed to two salts. Metal plus salt, single replacement. That means there's a possibility that the lead will become a 0. And the magnesium is going to then oxidize to the salt. Okay, magnesium is +2. Nitrate is -1 apiece. That's why you need 2 of them to balance it. Question is magnesium above lead on the reactivity chart? If it is, the reaction goes. Okay, so here's lead. And where's magnesium? So is magnesium above lead? Magnesium is above lead. Excuse me, not lead. Yeah, lead. This should be, yeah, magnesium lead. So is lead above magnesium or is magnesium above lead? Magnesium is up top, right? Okay, that means it's above lead, so the reaction is going to go. So yes. And the answer after you balance the equation is saying that magnesium is above lead. That's the reason the reaction goes. If it was the other way around, there'd be no reaction. Half reactions, we're going to take magnesium. Okay, that says solid or 0. Because it goes to the Mg +2, that means it's going to lose 2 electrons. Lead, going from the salt to the metal, gains those 2 electrons. Those are the 2 half reactions. So half reactions show the electrons moving. Okay, then you have your extra credit equation to balance. Does everyone know where that's located? Canvas, files, test, extra credit. Okay, so that's what you're looking at for tomorrow. A version of this. Now, test 3 is the most diverse of all the tests. Covered a lot of material. Test 4 is going to be very focused, and test 5 is going to be very focused. We're covering one thing for test 4. That's stoichiometry, nothing else. Test 5, we're looking at solutions, nothing else.